Professor Matsushita is already here.
Hi, how are you?
Good, how are you? Okay, I would like to it's my great honor to introduce Dr. Yasuyuki Matsushita. And Dr. Matsushita is a professor at University of Osaka, and he received his BS, MS, and PhD, and all from University of Tokyo. And prior to this position, he was with Visual Computing Group at Microsoft Research Asia for about 12 years, I think. He has very been supportive in the community's development. He's the editor-in-chief of International Journal of Computer Vision, IGCV, and also in the editor board of PAMI, Visual Computer Vision Journal, and many other journals. And is serving right now as the program co-chair of PSVT at 2010 and 3D IMPTV, which is currently 3DV in 2011, ACCV and ICCV 2011, and the general chair in ACCV 2014, and will be the general chair of ICCV 2021. I still remember during the time when he was a program chair of ICCV 2017, when he was very busy in organizing this conference, and he still takes some time to help review the papers in our workshop. He has already conducted extensive research in various methods for 3D reconstruction. Especially, he has pushed significantly development on photometric stereo, shape from shading, and some of his recent work has been applied using structure from motion and for calibration. I'm already very excited to see his talk today. Let's welcome for Dr. Matsushita's talk.
Thank you very much for very kind introduction. And I thank the organizers for having me in this workshop. From me, I'd like to share our recent work on light source estimation based on structure from motion. Okay, so let me begin with a little bit of context. In our group, we are interested in shape estimation from images observed under varying lighting directions. And suppose a static scene observed from a fixed camera. Then we can take a photograph under some illumination. Then we move the illumination only, then take another photograph. We keep doing this to observe, many different shading variations on the surface until we are satisfied. Then from such observation, we can obtain the shape in the form of surface normal. And this approach is called photometric stereo. So this visualization is basically showing the surface normal color-coded in RGB color channels. So for example, green pixel represents the surface looking upward direction, and magenta indicates that this surface point is looking at the right bottom direction. So this surface normal, the photometric stereo gives us a lot of information about the surface detail. For example, let's look at this video. Suppose we have a set of images observed under different illumination and also from different viewpoints. Then from this kind of input data, we can certainly apply some structure from motion or multi-view stereo in order to recover the shape. So that is something we call geometric approach based on triangulation. For this particular scene, without a lot of texture, it's not easy to establish the correspondence across different views. Therefore, geometric approach is not that great. But with photometric stereo, with photometric approach, we can recover very detailed surface. So for a photometric stereo to work well, we need to calibrate the light source directions or positions. Here is a very simple Lambertian image formation model, which is often used for photometric stereo. And of course, the goal is to estimate the surface normal N from a set of measurements M. This is a measured pixel intensity with the knowledge of the light source direction L. And in order to solve for surface normal N, of course, we need multiple observations and the different lights. But what's important is we need to calibrate the light source directions accurately, as good as possible, to recover accurate surface normal N. So this is why we are interested in light source calibration. We want to know the light source direction precisely, or light source position. And also the light source may not be directly observed from a camera. So that's the point, okay? So this motivated us to develop a simple and accurate point light source calibration method that we call light structure from pin motion. As you can imagine from the name, the method uses structure from motion for determining light source directions or positions. The work is done by my student Hiroaki Santo here, and my ex-postdoc Michael Bechter, now with Facebook, and the Professor Samejima, now with Amazon, and the Professor Sugano, now with the University of Tokyo. So these three people are gone, but this student is still with my group. Okay, so let me begin with the problem setting. So what we want to know, either the light source position or direction. So one is that there are two types of light sources that we consider here. One is something called nearby point light source, which is located near to the scene, so that we want to know the 3D position of the light source. The other type is directional light source. Point source located infinitely far away, so we only want to know the direction of the light source. In either cases, the camera may not observe the light source directly. Then how do we determine the light source position or direction? So this is a problem. There are some previous works to solve this problem. So one approach, one of the effective methods, uses multiple mirror spheres placed in the scene and observes the specular highlights on the sphere. Then, based on the triangulation, they can determine the light source position. Of course, we need to know the location of the spheres for doing this. Another method is also based on the mirror, but a planar one, whose pose is known by some marker, alcohol marker or something. By observing specular highlights at the different poses of the mirror plane, they can recover the light source position by triangulation. So these existing methods are effective, but they rely on specular highlights on the calibration target. Therefore, they need to detect the exact position of the specular reflection. However, since the camera observes the reflection of strong light, the highlight can become very wide, which makes it very difficult to determine the precise position of the highlight center. In addition, sphere-based method needs to know the precise position of the spheres. To achieve this, it requires to measure the sphere distance in 3D and fit ellipsoids to the sphere boundaries in the image, which is not that easy to do. So in our method, we therefore avoid spheres and highlights and instead use small shadows on the calibration target. In this figure, the left-hand side is just a camera and light sources. And the board on the right-hand side is our calibration target. The calibration target consists of a planar alcohol marker board and some needle pins randomly stacked on the board. Okay, this is, so I'm going to show you how this, this board can be made. So first we print the 2D marker on the paper and paste the paper on the flat board. After that, we pin needle pins on the board. As you can see, our target board can be made in less than 1 minute. An important point is that we don't need to measure the pin positions when creating this target. So pins can be randomly stacked on the board. So in a few minutes, from calibration target, why we can recover the light source positions or directions. So as shown in this figure, when we turn on the light source, we can observe the shadow of the pinhead. Like this. Suppose this light is on, and then it casts a shadow using this pinhead as a shadow caster. If we know the pinhead position, if we know this position, then we can easily compute the light source direction from this shadow position. So we are assuming that we know this shadow position because we know it's on the plane and we know the plane coordinates. However, the thing is that, so the important point is that it is not necessary for our method to know the pinhead positions. But we can just place the pin randomly. So we treat this pinhead position as unknown, but we can still recover the light source position or direction. Okay, but we move the calibration target in front of the camera so that it can observe the board under multiple different poses. So this is the condition. Okay, let's look a little bit into the mathematics. So we can regard the light source as an inverse pinhole camera. So here we have a traditional pinhole camera. And this camera projects the object point X to point S on the image plane. So this is a projection, right? Everybody knows about that. Now we replace the pinhole camera with a point light source. So instead of receiving the light through the point like a camera, it emits light from this point, light source point. As a result, it projects object point X to point S on the shadow receiver plane. Mathematically, both projections can actually be formulated in the same way. So 3D, 2D projection can be written using projection matrices. And so the left-hand side is the camera projection. and the right-hand side is shadow projection. So this is a camera projection and shadow projection, and they are mathematically the same thing. And the left-hand side is a camera projection model, and we all know that this is we have intrinsics made of focal length and the optic center, and similarly for shadow projection we also have intrinsics made of the position of the light source, and also we have extrinsics here, left-hand side, rotation translation. The similar thing for shadow projection, we can write the extrinsics of shadow projection model like this way. And if we take a product of these intrinsics and extrinsics, we have a projection matrix. This is for nearby point light source, and which looks like this. And for our directional light, we have a very similar projection matrix, but the only difference is, this part is 1 and this part is 0. Okay. Then, in camera projection, the problem of structure from motion is to estimate the projection matrix P and the 3D point X from known, observations S, observed image points S. So this is, called the structure from motion, as we know. And in the, our calibration method, we want to estimate the light matrix L, and also pinhead positions X, which is a shadow caster, from the shadow positions S on the shadow plane. Since this is so similar to structure from motion, we call our method light structure from pin motion. So as you can see, the problem setting is almost equivalent. Structure from motion wants to know P and X from known S. And in our case, we want to know L and X from known S. Okay. The solution method is also essentially the same. So we rely on bundle adjustment. So we minimize the reprojection error on the shadow plane, shadow coordinate. So which is just formulated as the least squares of the reprojection error. So here red variables are unknowns. Unfortunately, this is a non-convex problem. So how do we initialize the solution? Because it's a non-convex problem, we want to have a good initialization. If we have that, it is likely that we can reach to our good solution. So we begin with this equation. So there are two vectors. One is from shadow point to the light source, so which is green. So this forms one vector. And also a shadow point to the shadow caster point, which is blue in this figure. And they should be parallel. So that gives us a constraint like this. So the cross product of green and the blue vectors should be 0 vector. Then from this, we can establish a system of equations like this. And we don't have to go into the detail, but the important thing is that these red variables are something we don't know, and the black are that we know. This contains some second order terms, but we simply ignore these variables, and then we only solve for this first order variables. Okay, so to solve for, so we have now 6 unknowns, right? 6 unknowns, and we have a lot of equations. For this linear system, for solving this linear system, we need at least 5 poses. This is the conditions that we derived. So the number of poses required for solving this equation should be greater than 4 plus, 1 over n number of pins. Okay, so we can increase the number of pins, but it doesn't help to reduce the number of poses, essentially. So here I'm going to show some simulation experiment. And first I discuss the synthetic experiment. So here I show the result of experiment where we added some noise in the shadow detection part. So if there is no noise in detecting shadow position in the image coordinates, then the light source estimation is perfect, essentially. So there's no error if the shadows are correctly detected. And as we increase the noise level in the detected shadow locations in the image coordinates, then gradually the error increases. And the right-hand side is about the number of poses where so here we are assuming that we have some noise in detected shadow location. And then in that case, we analyze, increasing the number of poses, whether the increasing number of poses help. And it actually does. And as we increase the number of poses, the estimation of the light position becomes more stable. So the recommendation is that, as we always expect some noise in shadow detection, the more poses help. I mean, more observations of different poses of the calibration target, that actually help. Next, I explain our real-world experiment. We performed, under 4 different settings. And so E1 and E2 are nearby point light sources setting, where light source is close enough to the target. And E3, E4 are regarded as distant light source setting. So one uses sunlight, which is far enough. And the other is a flashlight located, sufficiently far away from the target object. So for nearby point light sources, we want to estimate the light source position. And for distant light, we want to know the direction. And here are some results. For this setting, the light source position estimation error was like 6.4 millimeters. And for this setting, it was 2.5 millimeters. And for direction, sunlight source estimation direction error was 1.1 degree. And for this setting, 0.5 degree. And here is some reprojection of the estimated light position in the image coordinate. And the blue is ground truth and red is our method, which shows, well, from my viewpoint, it's sufficiently close. Okay, so we also evaluated the pinhead position estimation. And here are mean error of pinhead positions. So they are like less than 2 millimeters in all the setting. Actually, the pinhead size that we have used is diameter of 3 millimeters. So this mean error is sufficiently small. And we did some comparison with the previous effective method. And it actually, our method works pretty well, as good as the previous work. Okay, so the conclusion is that point lights can be calibrated, just like in a camera case, using a structure from motion. And our calibration target is pretty simple and easy to make. We can make it really cheap. And I hope, if it is useful for any of you. So the code is available on somewhere, accessible from QR code. That's pretty much it. Thank you.
Thank you very much, Dr. Yasu. So we have several questions. Actually, this work is very inspiring, and because generally you switch from structure from motions camera pose estimation idea into the right now the light source calibration, and share quite a lot structure from motion, quite a lot concept used for structure from motion. Right now, you can apply to the light results calibration. Some questions from the audience and myself is: do you have the evaluation about the pin number? How many pins you need to? Is it something like using a single one and you apply you switch quite a lot of different orientations, but the checkerboard can still give you a good result?
We actually did, but I forgot the result. But if my memory is correct, the more the better. But at the same time, I kind of remember that it didn't help much. But you can refer to our paper. We definitely have that discussion.
Okay. And in structure from motion, normally when people have multiple using factorization based on structure from motion, after tracking for many frames, and when they later do SVD decomposition, and they have different solutions that makes that finally resulting in different scale. And in your calibration, do you have the scale issue?
We actually, let me recall that. No, we actually don't have the scale issue because we know the scale from the calibration target.
Yeah.
So we have the arco marker, and we don't have that scale issue thanks to the calibration target. So it's a easier problem compared to the general structure from motion because we know the reference object here.
So if we remove the AR code here, and do you think in this case will the calibration still work? Because right now you are mainly estimating the direction, and maybe for position estimation that may have a scale issue. But what about for direction? If you are just interested in what is the sunlight direction, in this case, do you still need the checkerboard?
We use the checkerboard for two purposes. One is to know the pose of the calibration target, and the second is to know the scale. Mm-hmm. And we definitely need to know the pose, even if we forget about the scale. And in order to, so as long as we have an access to the pose of the calibration target, we can remove this arco marker in order to achieve the calibration of light directions.
Okay. One question from the audience: what are the main results? What are the main results of the error? And is it from the detection or optimization?
It's actually detection. So detection of shadow is not that easy. So that's our experience. And quite often, we have some environment lights, and in that case, the shadow becomes really, blurry, and it's not easy to, accurately determine the center of the shadow. So that's a tricky part.
Okay. A follow-up question for myself is: when you try to do the optimization, do you for structure from motion, and when people do the optimization, they try to do SVD decomposition and then select the eigenvectors corresponding to the smallest selected 3 eigenvectors and remove everything else and make it as a 0? And do you do similar optimization?
We actually didn't do that. Is that, you know, assuming some orthographic projection? If you you describe the SVD and the finding null space, and then disregard the other part.
Okay, that is very inspiring. And you mentioned I remember you showed the result for different capture of the place. Do you have some idea, suggestion that how many numbers of the capture should be okay to get you a good calibration?
That's I'm really bad at remembering numbers, but that should be on the paper as well.
Okay.
But you know, nowadays you can record videos, right? So you can just move the target in front of the video camera, maybe less than 1 minute. Then you know you definitely accumulate a sufficient number of frames.
Okay. Yeah, I think that is pretty much most of the questions, and there might be some other questions on YouTube channel. And right now it's still about 100 people watching out the video, and we really want to thank you for your great talk. That is very inspiring. Actually, this idea I would say can be used for calibration. Maybe we can simulate this idea for many other tasks as well. And I would really think this is a very interesting and inspiring work. Okay, I would like to thank you again, Dr. Yasu.
Yeah, thank you very much.
Thank you very much. Yeah.